if you have two masses and they are moving in a, let's say in this room where I am, if only internal forces are acting within the masses, right, then we can say that the system is isolated. For example, there, right? But as soon as there is a contact between the masses, that's when you start analyzing the system as a whole, separately and as a whole. So system is isolated only if internal forces are acting on the system. However, as you see here, you may have different situations where an external force is acting, for example, on a mass, in this case an arrow, and that will give momentum to this arrow to travel with some velocity. So that's why at the beginning they give you this slide, because in here what you see is a game, a billiard game, right, where you have different balls, right? You hit the white ball, right? And then after it makes contact with the purple one, it transfers momentum and energy to the yellow one, to the number one ball. And then that ball travels. So we are going to be studying momentum and the definition of momentum, linear momentum, but then we will apply this especially to collisions. And there are different types of collisions, of course. And that is one of the goals of this chapter as well, is to understand how to analyze collisions and what happens when a collision is in one dimension, but what happens also when the collision is in two dimensions. So if only internal forces are acting between the masses, well, we have that the force on one due to 2 is equal to negative. It's sort of like the gravitational force between masses, between planets, or the sun and the earth, sort of like that. Okay, so in this case, we have that since the magnitude is the same and they have opposite directions, then we basically have an isolated system there. Okay, no external forces are acting on the body. So there is no net acceleration on the system, right? So if you apply Newton's second law for each force, you have that m1a1 plus m2a2 is equal to 0. And if you apply the definition of acceleration, right, you have that m, the first derivative of v1 respect of time, plus m2, the first derivative of v2 respect of time, is equal to 0. And then you have that equation, which by using your calculus derivative property, the derivative of the sum, you can combine into one derivative, and you have that the derivative of the momentum on 1 plus momentum on 2, because the definition of momentum is given by the equation there, m times the velocity. So keep in mind that momentum is a vector. All right, momentum is a vector and it's always on the same direction as the velocity. All right, the units of momentum are kilograms meters per second, right? So that is our notation for momentum, and we have this and the units. So joules was for energy, for momentum will be kilograms meter second, right? So it's a vector, it has magnitude and direction, and you will see when we start doing the examples or problems, how we use this concept to analyze different systems. Okay. But just to put it in a simple form, this basically relates with Newton's third law. For every action, there is an equal and opposite reaction. So if you hit a mass, that mass will receive the force and then it will gain momentum. We normally say that a body or a mass gains momentum because it's gaining some speed, which is the magnitude of the velocity, right? So what happens, for example, if you know that for a system, for an isolated system, let's just say of two masses, right? For an isolated system, if you have two masses, what the equation that I had here before was telling you what this is telling you is that P1 plus P2 equals to 0. And this, you can imagine this example as, for example, a kid, let's suppose you are on ice, right? This ice. And you have a kid that is standing on the ice, right? You have a kid standing on ice. And then you have his or her dad. If the dad pushes the kid, small push, the kid will move on this direction. But because of action reaction, the dad will move on the opposite, right? Because the force that he's exerting to the kid is going to be there's going to be a reaction on his hands, making him recede. With momentum is that the momentum of the kid plus the momentum of the dad is equal to 0. But the dad, right, let's say here M1 is greater than M2. So a typical question in a standardized test that I have seen several times is which person, right, which will move a farther distance? And it will be the kid, because the kid will gain a greater speed. Right? Because of this equation, we know that P1 is equal to minus P2. Now, the minus is just in terms of the direction of the vector. If I take the magnitude, P1 equals to P2. So the momentum of the dad has to be equal to the momentum of the linear momentum of the kid. So in order for that to be equal, if this is true, then V1 has to be less than V2. So the kid will move a greater distance. Right? Now let's analyze what happens if you take the derivative of momentum. So let's say you have a mass, just one mass, and you know P equals to mv. Let's suppose I want to find the rate of change of momentum. So mass is always constant, except for the last bits that we're going for the last model that we're going to study at the end of the class, which is rockets. But for any bodies, a mass, a ball, a cannon, anything, it's just constant, right? So the derivative is applied here. And we know this is acceleration. So mass times acceleration is the first derivative momentum. So basically, what you have here is Newton's second law. That's what you have. When you apply the first derivative of. And what is mass times acceleration though? So the first derivative of momentum respect of time is equal to the external force acting on the mass. So that's another way of writing Newton's second law, that the change of momentum of a mass is due to external force acting on the mass. And we know that the momentum will change if the velocity changes. Algebraically, what you have in there is that the change of momentum is equal to an external force times time, because this is what you can do. Change of momentum respect of time equals to the force if I multiply there, delta P there. Delta P is P final minus P initial. And we call all this the impulse. That is basically one of the important results when we analyze the change of momentum. We can apply that for collisions, for example. Right? So obviously, since a momentum is a vector, right? You can have a particle moving in 3 different directions. So it makes sense that you have momentum in 3 different directions. So that was Newton's second law. And this is the equation that I just proved on the whiteboard. So it's also on the slides. The change of linear momentum of a particle is equal to the net force acting on the particle. And it makes sense, right? Because we know that an external force produces an acceleration, and the acceleration is a change on velocity. Two objects have equal kinetic energies. How do the magnitude of momentum compare? So let's suppose you have two objects with the same kinetic energy, but they don't tell you anything about the mass or the speeds. So you can say that you have object 1, and this can be an object 2. We say that kinetic energy on 1 is equal to kinetic energy 2. But kinetic energy of 1 is say this is 1, say this is 1/2 m1 v1 squared equals to 1/2. So the only way you can tell anything about momentum is if you know anything about the masses, or at least the velocities. You don't know anything about them. So you don't have enough information to know how does P1 relates to P2. You don't know. Okay, they will have to give you something else to work on. So that will be the answer for that question there. Not enough information to tell. Okay, this is another good example about momentum. And I talk about this also when we were talking, introducing or discussing Newton's laws. So it says that your physical education teacher throws you a baseball and you catch it. But then he's throwing you a medicine ball. A medicine ball in the gym is a big, heavy ball that you use it for exercise. And it says there, right? The mass is 10 times the mass of the baseball. You are given the following choice. So you want to catch the medicine ball from the easiest to hardest to catch. So you are given A, B, and C. You have to choose which will be the easiest and which will be the hardest. So if you have a medicine ball that is 10 times the mass and you throw it with the same speed as the baseball, it will be very hard to catch it. It will actually hurt. So the same speed will be the hardest. So then you are left with momentum and kinetic energy. Which one will require the less amount of effort to stop it, right? So this is what you do. What you do is you write, you can give values if you want, but say that M1 is 10 times M2, or M of the baseball, M of the medicine ball, right? The momentum of the medicine ball, the magnitude, is the mass of the medicine ball times the velocity of the medicine ball. Speed. The momentum of the baseball is the mass of the baseball times the velocity of the baseball. Okay? Now, if you want them to be equal, you will make this equal to this, but we know that this is this. So the velocity of the baseball will be, wait, it is on the problem. Mass of the baseball. Oh, yeah, that's fine. 10 times the velocity. Yeah. Medicine ball, velocity of the medicine ball. Yeah. So the velocity of the baseball will have to be, or the velocity of the medicine ball will have to be a tenth. So not bad, right? If you have the same momentum, the same linear momentum, the medicine ball will have to be basically 10%, right? Of the velocity of the baseball. Now, what about if they have the same energy, the same kinetic energy? So for energy, for kinetic energy, 1/2 of the mass of the baseball times velocity of the baseball squared is equal to 1/2 mass of the medicine ball, speed of the medicine ball squared. But we know that the mass of the baseball, mass of the medicine ball is 10 times that. So, well, first we do this. Mass of the baseball, velocity of the baseball squared equals to 10 times mass of the baseball, velocity of the medicine ball squared. This cancels, and then if we take the square root, the velocity of the baseball will be the square root of 10 times the velocity of the medicine ball. The square root of 10 is approximately 3.3. And this was 10. So the velocity of the baseball here divided by 3 0.3. So the medicine ball will go at a higher speed if they have the same energy. That means that it will be harder to catch it if they had the same energy, and easier if they had the same momentum. So the answer for that question will be momentum, energy, and speed. There it is. Now, if you get confused with the variables, you can always give values to the masses. So that's what we just did. For an isolated system, the change of momentum is 0. Okay, that is when the external force acting is equal to 0. So if you have two masses approaching, right, even though each mass, for example, in a collision, for any collision, since we know Newton's third law that says that for every action there is an equal and opposite reaction, when one of the masses crashes, or if there's a collision between two masses, the forces will cancel. So the external force is basically 0. That means that in a collision, the momentum of one, the change of momentum of one is equal to the change of momentum of two, or what you have right now on the screen, which is that the momentum of one initial plus momentum of two initial equals to momentum of one final plus momentum of two final. Okay? That all comes from this idea of a system that is isolated. And again, you can extend that for every direction. That's basically what I said. So how will you do a problem then? Before we get into collisions, we have to analyze problems like that. So a 60-kilogram archer is on ice and he's firing a 0.030 kilogram arrow at 85. Remember that 85 meters per second, according to the picture, will be to the east, right, to the positive x-axis. What's the velocity of the archer? That's actually very easy. So you have that the archer which is on ice will shoot an arrow towards the right with 85 meters per second of speed, or 85 meters per second velocity. The mass of the arrow is now this guy is moving to the left at 60 kilograms. And you want to find this. So, two ways of doing this. P1 plus P2 equals to 0. If I do it on the vector form, I'm going to say that this is 1, or let's say the arrow and the adult, the boy, the person. The moment of the arrow would be mass velocity, right? Let's go to the next slide. Mass of the person. So velocity will be negative. If I do the math, I get minus 4.25 minus 4.25 I centimeters per second. Clearly it has to be in centimeters per second because it will be very small, right? It will be 0.0425 I meters per second. So we just put in centimeters per second. The other way you can think about this is with magnitudes. You only have two bodies in that system, the archer and the arrow, person and the arrow. So in terms of magnitudes, you can just say that the magnitude of the momentum of the arrow is equal to the magnitude of the momentum of the person. You can just do it like that. And you get the same. Or with the speed. You just have to remember that the person will move to the left due to momentum, right?